Okay, this is a little lesson on the derivative of y equals log x. Something that you just need to memorize, really. So when you have y equals log x, your derivative is 1 on x. Now, I just want to look at this in an intuitive way first. What I mean by that is, if we look at the graph, y equals log x, and we look at the graph of its derivative, you can see that they fit together really nicely. So here's your log graph, something like that. You can see here in this region of the graph where x is between 0 and 1, the slope is very steep uphill, right? So if I was graphing the derivative, at that point I'd need to be up here somewhere, right? Right, so if I had, say I put 1 about there on this graph, between 0 and 1, the slope is really steep uphill. So we'd have values, we've got y equals the derivative here. We'd have very high slope values, okay? As we come over to this part, you can see y equals log x, the curve is flattening. It's still a positive slope, but its value has reduced a lot, right? So here it's really steep, positive. Here it's not very steep, like I'll say shallow, but still positive slope, right? So we'd be up here and then we'd have to come down, but still stay positive. We're looking at a curve like this, right? Now there's a function that you know of that does that, and it's y equals 1 on x. Right? You would normally draw it, excuse my poor use of this pen. So it's tricky to draw, I'm sorry. You know this rectangular hyperbola graph and this function, and you can see, oh yeah, well, what I need for the derivative matches up pretty well with this. Obviously we don't worry about that part because we can only log positive numbers, right? I think there's something in the book about the domain of your derivative usually comes from the domain of the function. So if you can't have a function with negative x's, there's no point thinking about the derivative for those negative x's, right? Sometimes the derivative can be even more restricted, but usually those domains will match up pretty well. Okay, so hopefully intuitively it makes sense. I'll just quickly run through the implicit differentiation. It's not part of our course, so I can't say I'm massively up to speed on implicit differentiation, but because I don't currently teach it, but the book does mention it. You don't need to know the derivation, you just need to memorize that the derivative of log x is 1 on x. How do they do it in the book? They say, all right, if we've got y equals log x, what that means, if I rewrite this, I'm in base e, my power is y, and the answer to this exponential would be x, right? how can we find the derivative of this? Exponential, well, we could maybe give it a go. It's a little bit tricky though. And the reason for that, so we need the derivative of x dx, which will just be 1. So derivative on this side's easy, derivative of x is 1, but what about this derivative of e to the y? Well, we know the derivative of e is itself, right? And we know that y, so this is like, at this point it's like we're using the chain rule. So we're saying normally if I had, I don't know, y equals e to the 3x or something, and I found its derivative, I'd say, all right, well, derivative of e is itself, and then I'd go to the inside of the function, right? So I'd treat it as a chain, right? And I'd multiply by 3. And we do the same thing here. It's just that we don't really, like we can't really get to y in terms of x's. So what we know that y is dependent on x's. We know it's a function of x, but we can't express it in terms of x. So what we're stuck doing is just saying, well, the derivative of y is dy dx, right? So just run through that. We're trying to find the derivative of e to the y, right? We use the chain rule like we normally would. We know derivative of e to anything is itself, and then we have to look at the inside and think, well, what's the derivative of the y? So, well, unfortunately, there's some situations where you can't write the y in terms of x's. I'll show you another example in a minute, actually, because that might seem a bit odd at the moment. So what you do is you just say, well, I know that y has a derivative with respect to x, and we'll just write that. So then with a bit of rearrangement, you say, okay, it's 1 on e to the x, but I've already defined e to the x as being, e to the y, what am I doing? Need more coffee or something. So I'm just dividing both sides by e to the y here, rearranging. But then I've already defined e to the y as being x, so I'm going to sub that back in. So therefore, right. So that's how we would do a derivative like that. Implicit differentiation comes up. The classic example is when you have a circle equation. Maybe I can think all right, so which really is coming from the distance formula, because circles need, how do we describe a circle? We need to have a center point and a constant distance for all the points around it, so we can draw that circumference. Maybe the simplest circle I can think of would be the unit circle, where you've got ones everywhere, where the radius is 1. And we just, using the distance formula really, applying Pythagoras. So you've all seen something like that before, but how do you express this equation? In fact, we don't call this a function, as you already know. We say it's a relationship because for every x, you get 2 different y's. Right? You could do your vertical line test. I put in x is a half and I get 2 values of y. Plus or minus root 3 on 2. So you can see that in the algebra as well. If I start rearranging and I take the square root of both sides, I get 2 answers, one positive, one negative. So how do you differentiate this? And what you do is implicit differentiation. So you say, all right, I've got y squared. I can't write the y in terms of x's, so I'm going to deal with the squared like I normally would in a chain rule. I'll say that's 2y to the power of 1. And then I'm going to say the derivative of the y is dy dx. Okay? So you you do like your outside and then your inside, and put those together. Then over here you can do the derivative. Derivative of 1 is 0. Derivative of minus x squared would be minus 2x. And then you do some rearranging, and you get minus 2x on 2y, which is the same as minus x on y. And if you want to work out the slope anywhere, maybe we could do it. Maybe I'll just look at, I don't know, what about a 30-degree angle? Or a pi on 6, if we're working in radians, where we have root 3 on 2 as our y, as our x, and half as our y. And if I was thinking, what's this slope coming through here? At that point, obviously it's negative, and I could work it out by doing the minus x divided by the y and find out that it's negative root 3, right? So you don't need to know this technique. I just wanted to very briefly run through it for those of you that are interested. Okay, how are we going to use it? Now the book's examples are pretty good, so I'm going to use their examples. They give you what looks like 2 fairly easy examples, and then they give you a harder one. So let me have a look at that.